I've had countless letters from people asking me about astronomy as a career. What qualifications are needed? What are the prospects? And anyway, what does an astronomer do? Well, I can assure you that your professional astronomer doesn't spend all night in a lonely observatory looking at the stars. Now, I'm an amateur astronomer. I always have been. And like many amateurs, I have my own observatory. But here, at the University of Birmingham, there's a department dealing specially with the needs of students who want to become professional astronomers. The Professor of Space Research at Birmingham University is Peter Wilmore. What do you look for instinctively in a student who applies for a course in astronomy?
Well, of course, enthusiasm for the subject and a readiness to work hard and, of course, some proven academic ability.
What about background studies? What should you have studied at school or college?
Well, at A-level, the important thing is to take physics and maths because they're the basis of any physics or astrophysics course. Many universities require you to take at least one other subject, but here, for example, we don't really mind what that other subject is. And taking AS levels is something that universities in this sort of area are gradually getting to grips with.
You know, I have many letters from young people saying, I'm interested in astronomy, what degree should I take? And I very often say, take astronomy by all means if you're 100% certain. Otherwise, take your basic degree in physics, where that gives you a broader background, and there's still an entree to most posts in astronomy. Does that make sense?
I think that's a very good idea because it does open up a wider range of eventual careers. But nowadays, most physics courses contain some astronomy or astrophysics, and there are a few, like the one here at Birmingham, the Physics with Astrophysics course, which contain a high proportion of astronomy and astrophysics, not so much as a way of training astronomers, but because we think this is an excellent way of training physicists. But on the way, of course, they do learn a great deal of astronomy, which then prepares them for a career in that subject.
When and where does your first-year astronomy student begin his practical work?
Well, they actually start working in this laboratory, which we call Astrolab. We have a collection of sky survey photographs from all over the world, from Mount Palomar, from the UK Schmidt in Australia, and also from Chile. So in fact we have a complete collection of the whole sky, so we can see every star in the sky if we want to. We've got an experiment that some of the students really hate, which is looking at a globular cluster. There we've got hundreds of thousands of stars in a cluster, and we ask them to count the number of stars in the cluster. Not just because it's terribly painful, but it's an interesting exercise because we ask them to find out the distribution of stars in the cluster. And even though they appear to be concentrated very closely together in a very tight mass, rather like a lot of bees buzzing around one another, they're actually distributed in a great volume of space. Most recently, we've actually received a plate from the Anglo-Australian telescope of the supernova, and we have a series of light echoes. The supernova has exploded, and the light has gone out into space at the velocity of light, and as it struck a couple of sheets of material, then the light has been bounced back and is seen a few years later. And by measuring the diameter of these rings, we can actually work out the distribution of dust in space and find out a lot about the material in the Large Magellanic Clouds.
So this really is in Astrolab, this is really the first step for practical work. And what comes after that? What's the next phase in their education?
Well, they also have an opportunity in the second year to work at the laboratory where they can design their own experiments, design their own equipment, which they will build in a laboratory like this, and then they will take it out to the University Observatory where they can make their own observations.
Here at Birmingham University, we have a telescope with an aperture of 16 inches or 0.4 meters. Now that's comparable with a telescope in my own observatory, but this is different because it's adapted specially for university use. It can carry out the same types of observations as those carried out with the giant telescopes at major observatories. Of course, it can't see such faint objects, but the principles involved are exactly the same, and that's what matters.
One of the main things we use the telescope for is spectroscopy. One of the reasons for that is that even if the conditions aren't perfect, then we can still get some very useful results. The telescope's equipped with a spectrograph, which allows us to look at the light from stars or galaxies, disperse it into the colours, and then analyse that using a modern detector. In fact, we have a CCD, which is the same type of device as is used on major observatories around the world. So we actually have, although the telescope's rather small, we actually have state-of-the-art detectors instrumentation on the back of the telescope. And it's for that reason that we can actually still do very useful work. In fact, we're here this afternoon setting up for an observing run. So what we'll be doing is to set up the spectrograph, make sure we're looking in the right part of the spectrum, and doing a few calibration runs just to make sure that everything's working properly.
Well, what this project is about is we're looking at a binary star called B Auriga, and by looking at the star, we're observing the splitting of it with spectral lines. In this case, this is a hydrogen spectral line, absorption line that is. And the reason why we're looking at the absorption lines is because the stars are so close together that by using telescopes, we can't tell that there is two stars there rather than one. Now, the reason why this is split is because of the fact that the two stars are rotating around their common centre of gravity. And when one is moving towards us and one is moving away from us, then the light is, as we say, redshifted. If, of course, both stars were moving sideways, i.e. they were one behind the other as seen by us, we wouldn't see any splitting here because there wouldn't be any component of velocity in the direction away from us. And by looking at the amount of splitting, you can work out the velocities of the stars.
Here we have, in the third year of our course, about 12 students get together and look at a particular topic of interest. This year the topic is imaging, and we're looking at different ways of forming images. We have 5 experiments this year. The first one is a radio interferometer. This consists of 2 radio dishes working at 21 centimetre line, and the students actually outside at the moment setting that up to try to make some measurements of the angular size of the sun.
We just have to increase the time difference the next time we do it.
Another experiment involves using a CCD camera, which we've built in the department, and they're trying to capture images of stars and then analyse the images and massage them to get rid of defects, this kind of thing. We are also interested in speckle interferometry. This is a technique where we can try and get rid of the atmospheric degradation that the Earth's atmosphere produces.
When starlight arrives at the top of the Earth's atmosphere, the light waves are assumed to be playing parallel, but because of temperature gradients and turbulence in the atmosphere, they tend to be distorted. And so rather than the perfect diffraction-limited image from the telescope, we get a speckle pattern, and each of these speckles is an attempt by the telescope to reach the diffraction image. What we're going to do is grab each frame of the speckle pattern, transform it, and add lots of the transforms together, and then transform them back again. And by doing this, especially for a binary star, we can resolve it, whereas using a telescope normally you wouldn't be able to resolve it.
Another experiment is looking at the twinkling of stars. Stars twinkle because of irregularities in the Earth's atmosphere, and they produce a shadow pattern which moves across the Earth's surface.
Well, the experiment we're doing is measuring the velocity of a turbulent layer in the atmosphere. And so what we do is we take 2 apertures and measure the time that a feature in that turbulent layer takes to go between the 2 apertures. Now we do that by taking readings from first one and then the other. So we have to swap quickly between the 2, and we use this rotating disc for that. What we're doing now is we're trying to work out how fast we can get the rotating disc to go. So we're doing that by flashing a strobe light onto the disc. And when the rate of the strobe light matches the rate of rotation of the disc, it'll freeze the motion of the disc, and then we can work out from a readout on the strobe how fast it's actually going round. And so that gives us a readout of about 950 RPM. And so we can build that gradually up to get as fast as we want.
The 5th experiment involves imaging with coded masks. This is a technique which is used in our department in X-ray astronomy, and we're now trying to apply it in a laboratory situation.
What happens is you have a source of light, such as this here, illuminates a mask, which is placed on the front of the TV camera here, and the detected image is displayed on the monitor here. Now, the picture on the TV screen shows the shadow that the mask produces with a single point source. If we switch to another point source, which is slightly displaced off axis, then obviously it will produce the same shadow, but displaced slightly on the detector. Now, with 2 sources on at the same time, you see that we have 2 shadows that are displaced slightly, one from the other. And if I change the separation between the 2 sources, you see that the 2 shadows move with respect to each other. Here we have just 2 sources, and each of them produces its own shadow. If we have more than 2 sources, each of them will produce their own shadows, and we can see how many sources there are by how many copies of the shadogram there are on the detector.
Well, you've seen the coded mask principle being explored by students in group studies. It's particularly intended for use at X-ray energies and low gamma ray energies, where there just isn't any other way of taking a picture of the sky with a telescope.
And you built some of these here?
We built 2 of them to go into orbit. The first of them was on the NASA Spacelab 2 mission in 1985. That instrument was taken into orbit and operated for about 10 days, and then finally brought back, and we refurbished it and had hoped to fly it again this year. But in fact, the Challenger disaster meant that hasn't happened, and we're now hoping that we may be able to use it in the run-up to the space station. The second one was placed on the Mir spacecraft of the USSR. That's a space station, in fact, and is intended for long-term operation in space, and so we hope that telescope will go on operating for a considerable period, and it's already been operating for a couple of years.
So the students here were involved in this kind of work from the outset?
Yes, that's an important principle. You've seen that the coded mask telescope principle is used in teaching undergraduate students. Then, when students become postgraduate students, they will form part of the team that build and operate these instruments and get further training from that. And then, of course, in using the telescopes, we are carrying out our own research. And so the training of undergraduate students and postgraduate students and the carrying out of research are all closely linked in what I believe is a very fruitful relationship.
What about the testing of equipment?
Well, that's a very long and important process. It takes, in total, a few years of testing before something is actually launched. And even before that, there will be testing and calibration which has gone on in our own laboratories. We have to have equipment which will enable us to calibrate an X-ray telescope in the lab, since our ability to do that in orbit will be restricted. And we have equipment which enables us to take electronics, for example, at high and low temperatures in a vacuum and operate it for a week or so and see that it has the capacity to operate in the rather rigorous conditions that it will encounter in orbit. There's a lot of experience which has been built up over the last 30-odd years in what sort of tests are essential, and we go through a standard sequence which is usually prescribed for us by the people building the spacecraft, and these tests are all well known, and we know the ones that are going to cause the troubles.
Then, of course, there's Starlink. I think not everyone may know what Starlink is.
Well, that's the final stage of the process. The last job that has to be done is to use these instruments to get scientific results, and that's where Starlink comes in.
What exactly is it?
It's a computing network which is run by the Rutherford Appleton Laboratory and is used by all astronomers, never mind which waveband they're working in. In the UK, there are about 1,000 users at the present time. The various computing sites, or nodes as they're called, are not confined to the UK. There are also nodes in many other countries abroad, and this means, for example, that it's possible for an astronomer working at his desk in the university here to routinely interrogate databases of astronomical information, for example, in Holland or in the USA.
When do the students here really start to use Starlink?
Right from the beginning. It's something that they get exposed to as soon as they start their postgraduate work, and maybe even a little bit before that.
One of the unique features of the course is group studies, which happens after the final examination. Here, our groups of students get together and present their own research as a group. They meet regularly and give mini presentations on the way their work is going. Other students may ask them questions, but it's a group activity.
The idea of this project is basically to get CCD images straight away from the CCD rather than using the spectrograph or anything. Focused down by the telescope straight onto the surface of the CCD. And then we take the electrons thus produced into the computer, stored as data in a file, which then, with a control program, will be plotted up in the front there. After that, you can take a block up to 256 by 160 in size and store it onto floppy disk or hard disk or whatever for further use.
When a student finishes his course and has graduated, he may well stay on to do some research, as Simon Duck has done. Simon, what are you actually doing now?
I'm a PhD student studying cataclysmic variables and using the ROSAT satellite.
What exactly is ROSAT?
ROSAT is an extreme ultraviolet and soft X-ray satellite, which is a joint European and American venture, which will be going up next February.
And what do you feel you got out of the course here?
I feel I've got a fairly combined physics and astronomy background, and especially with the group studies, I got a very good leading into the PhD course.
What are your long-term prospects?
I'd like to stay in astronomy and do research at either this or another university in Britain.
This university has been running the physics and astrophysics course for several years now, and it's worth thinking about what all of this adds up to as far as we're concerned. Obviously, we are carrying out research in astronomy, and we are also training students to become astronomers. On the other hand, most of the students that come here go and do something else, and it's essential that we should provide them with the range of skills that makes them good employees in industry or in commerce. And if they leave here able to do only the things that would make them astronomers, then we should consider that we've failed in our job.
Finally, Peter, what do you feel about the future of astronomy in general, and British astronomy in particular?
Well, I'm broadly optimistic. There has been very serious pressure on basic science in the UK generally over the last few years. Astronomy has actually managed to withstand that fairly well, and I think that reflects something about the vigour and interest of the science which it produces. I don't see any reason why that should decline. We have excellent facilities as a result of the investments of the last few years, and I believe that the subject is in good health and will continue to produce good results. The area of weakness and the area of great concern, I think, particularly to people in universities, is the shortage of posts in universities. I hope that that is something which in the course of the next few years will improve, because I think that is crucial to a lively university astronomy in the next decade.
Peter, thank you very much. We've looked around the university department. We've seen how a student comes into astronomy and what he sets out to do. Obviously, not all the students we've seen are going to be professional astronomers. But even if not, what they learn here will guide them in the directions they eventually mean to take. And remember, too, that your student of today is your researcher of tomorrow. And if you're going to make a career out of astronomy or any other branch of science, you've got to be very clear what it means and also how you're going to tackle it. And that's what this course here at Birmingham is all about. Good night.